Hi, my name is Bernd and I would like to give a talk about analog computers in general, demonstrate how these are programmed and give some examples of how to produce oscilloscope pictures of chaotic attractors like a Chua or a Lorentz attractor, and will give a short background on the history of analog computing in the following. Now, what is an analog computer? An analog computer is a completely different beast compared with a digital computer. A digital computer is programmed with an algorithm, basically a step-by-step definition what is to be done when. For example, add two numbers and jump if the result is 0. An analog computer, on the other hand, has no program as such, but is programmed by interconnecting a variety of computing elements, which you can see here, for example. This is a historic machine. This is the first analog computer built by Telefunken in the years 1953 to 1955. And you can see you have a lot of computing elements. For example, these elements can be switched to compute the sum of some values or the time integral, or can be used as open amplifiers for inverse functions or the like. You also have, for example, multipliers. This module performs multiplication. You have function generators if you need some arbitrary functions which you cannot generate mathematically in an easy way. And the idea of an analog computer program is now to set up an interconnection scheme between these modules so that the modules perform the mathematical equation which describes the problem you want to solve with an analog computer. One of the main advantages of an analog computer is its high energy efficiency. Typically, an analog computer using voltages or currents to represent values exhibits a much better energy efficiency than a modern digital computer. This comes at a price. The precision is relatively limited with an analog computer, and you cannot easily extend the precision as you can do with a digital computer. Typical figures of precision in an analog computer are about 3 or maybe 4 decimal places. But for most applications, this is way enough precision to represent values, since, for example, if you take engineering problems, you rarely have measurement values with an accuracy of more than 3 or 4 decimal places. So typically, the limited precision of an analog computer is sufficient for most of the problems. When Telefunken realized in the second half of the 1950s that there was actually a market for analog computers, they decided that the machine you have just seen should be the first and last vacuum tube-based analog computer manufactured by Telefunken, and then decided to develop a transistorized analog computer, which was a pretty bold step back in the second half of the 1950s. What you can see here is unfortunately only the empty shell, but the shell of the prototype of the first transistorized analog computer in the world. You can see the basic construction is pretty similar to the vacuum tube-based system you've seen before, but this system already was fully transistorized with only the oscilloscope tube being an actual vacuum tube. Based on this transistorized prototype, Telefunken now developed in 1959 these tabletop analog computers. These models were called RAT 700, German für Rechner Analog Tisch 700, and sold very, very well in the late 50s and early 1960s. That was the first time that an analog computer was small enough and cheap enough to be bought, for example, by a university institute, so that hundreds and thousands of students could get their first experiences with analog computers of these models and makes. Telefunken continued this series of tabletop analog computers well into the 1970s, and they basically differ mainly with respect to the computing elements and the mechanical construction. From an electronics perspective, these machines are pretty similar to each other. In the 1960s, there were quite some companies who offered tabletop analog computers. By the way, tabletop is a little bit of an exaggeration. A typical Telefunken tabletop analog computer weighs about 105 kilograms. So it is not simple to find a table which actually supports a machine like this. What you can see here is another German brand, GTE, Goldmann Technische Elektronik. They built very, very nice tabletop analog computers as well. There were Japanese tabletop analog computers. Here you have a Hitachi system, which is also fully transistorized, and there were plenty of manufacturers, and the largest manufacturers for systems like these were apart from Telefunken, especially EAI, Electronic Associates Incorporated in the United States, but there were also a plethora of companies in France, in Great Britain, in Germany who offered simple or not so simple tabletop analog computers. So the first equation describes how the variable x changes with time. And you see the change of x is described by a constant c1 multiplied with the difference of y and x and some function of x. The second equation shows how the variable y varies with time, and y varies with constant c2 multiplied by x minus y plus z. And the third line shows how the variable z varies, and z varies just with minus c3, another constant, times y. And a system like this is called a system of coupled differential equations. These are differential equations since you have in one equation as well the naked unknown, so to speak, an x or a y or a z, and one or more time or other derivatives. In this case, we have ordinary differential equations since all our derivatives are with respect to time. The central part of the Chua oscillator or Chua attractor is this strange function f, which you can see here. It's labeled with 4 in the application note. And you see the f contains two absolute value functions, the absolute value of x plus 1 and the absolute value of x minus 1. And this f is fed with the variable x and is the right part of the right-hand part of the differential equation describing the change of x with time. So this describes the mathematical structure of a Chua attractor. What you now need to know are the particular coefficients which are required to generate the desired behavior. And these can be seen here. C1, for example, is 15.6, C2 is 1, and C3 is 28. And you also have values for M0 and M1. And here at latest, things start to become a little bit complicated. With an analog computer, which works with voltages or currents representing values, your values are restricted to a certain interval. And typically one thinks in an interval of -1 to +1. So regardless if you have a transistorized analog computer, a highly integrated analog computer, a vacuum tube-based analog computer, from a programming perspective, you always think of every variable being in the interval of -1 to +1. The problem here is the coefficients alone are way outside a suitable interval, and the same holds true for the actual variables within the problem. So, as stated here, the Chua attractor cannot directly be implemented on an analog computer. What is necessary is a so-called scaling step. Scaling is the operation which you perform to make sure that every variable within a problem setup of an analog computer will neither leave the interval of -1 to +1, nor will the absolute value of this value being represented by a voltage or by a current too small. What you want is values which use most of the allowable interval to get the utmost precision out of your computing elements. The scaling process is typically pretty involved. This especially holds true for chaotic systems like the Chua attractor described here. So I won't go into any detail here. If you are interested, you may find a more detailed description of the actual scaling process in the application note, which I refer to. But when we assume that the scaling operation has been completed, we can now start to set up an analog computer program. And programming an analog computer means, as you already know, to interconnect the various computing elements so that they build an electronic model of the underlying mathematical problem. The figure shown here, which is figure 1 of the application note, shows the subcircuit which represents the first equation of the original problem in its scaled form, which describes how the variable x changes with time. At first glance, this looks pretty involved, but actually analog computer programs are pretty simple to read and even to set up. What you see are three different computing elements. You have triangular elements on the left or in the middle. These are summers. A summer can have various inputs and yields the sum of the input values with a possible multiplication by a fixed input weight at its output. As a side remark, summers and integrators both perform an implicit change of sign. This is due to the actual implementation. So for example, if you sum the two values 0.2 and 0.3, you will get minus 0.5 at the output of a summer. The circular objects in this computer setup diagram are the coefficient potentiometers. A coefficient potentiometer is basically nothing else than a voltage divider, and this voltage divider will just be set to a value between 0 and 1. Being 10-turn potentiometers, you can safely assume that you are able to set these potentiometers to 1 part in 1,000. The most interesting computing element of an analog computer is the integrator, which is the second element from the right in figure 1. This is an integrator. Its symbol consists of a triangle with a rectangular part on its input side. And you see it has a connection like a summer coming from the left, but it also has an additional connection coming from top. And this top connection sets the initial value of our integrator. If you remember the integration process as taught in school, you may remember that if you have the integral over something and you have the antiderivative for your function, you always can add a constant c, and this constant c is basically the initial condition of our problem. Without the ability of introducing any initial condition, our analog computer setup would just sit there and do nothing, since all integrators would start with a value of 0. But to actually start a computation, you need at least one value which introduces something into the analog computer setup so that it can, for example, oscillate in the case of our Chua oscillator. The next figure in the application note, figure 2, shows the partial computer setup for the equation describing how the variable y varies with time. And you see this also consists only of summers of coefficient potentiometers and integrators. Now let's have a closer look at the patch panel itself. What you can see is the patch panel is basically set up of a number of pretty similar quadrants. There are 10 of these, so the name is not really appropriate. Each of these subsections consists basically of 3 computing elements which can be set up to perform a summation or to perform an integration, depending on where this plug is introduced. Now it would be an integrator, and this way it is a summer. Each of these elements consists of 2 columns of connections, and green connections are inputs, orange connections are outputs. The yellow connections with the diagonal stripes are connections for, in this case, servo potentiometers, SP, and we also have manual or hand-driven potentiometers called HP. You also have some free elements available, for example diodes, which come pretty handy when you need something like an absolute value function, and you have function generators, for example, for implementing multiplication operations and the like. These are implemented here. This, for example, this set of connections forms one multiplier and this forms another multiplier. The actual program uses several colors of patch cables. This makes troubleshooting way simpler. And to be honest, it is simpler to implement an analog computer program as it might look at first glance. It's pretty self-explanatory, and if you once have an understanding of how your particular machine is configured, it's really pretty easy to transform the analog computer program written down as a schematic to an actual analog computer program on your patch panel. All green patch cables represent the central function f of x. And as you can remember, it involves two absolute functions and a lot of summers and several coefficient potentiometers, so f is pretty involved. The red part, you see there are way fewer red connections than green connections, is the subcircuit for the variable x. And at the bottom, the black part is the sub-circuit yielding the variable y. I've already set up all servo potentiometers which are required for the actual Chua attractor, and we can now start the analog computer to actually generate a Chua attractor on the oscilloscope screen. You can see here the manual operation panel of the analog computer, and currently the system is set to pause. This means that all integrators just will set their outputs to their respective initial input connections, and the machine is configured for continuous computation. I could also select, for example, repetitive operation or iterative operation, but for the Chua attractor I will just run the computer in continuous mode. To start the actual simulation or computation, as you like, I just press the compute button here, and this will instantly display the wonderful so-called double scroll attractor on this oscilloscope. If you take a long-term exposure of this oscilloscope display, you will really get a mesmerizing display of a Chua attractor. And you can see it is truly a chaotic attractor, and the analog computer is currently running in high speed. That is an interesting point which deserves some background information. So just using these connections, you can select every integrator from exhibiting a time constant of 1, 10 meaning 10 times faster, or 100 meaning 100 times faster. Large analog computers typically had a special key labeled 10 times, which you can see here. And when you depress this key, this will cause a set of relays to switch all integrating capacitors to another set of capacitors, which is smaller by a factor of 10 than the standard set of capacitors. So if you patch, for example, all integrators within a computer setup to 100 times the normal speed and depress this key, the integrators will run in 1000 times faster than real time. So you can span a pretty large amount of time scales just by selecting which capacitor being used in your integrators. I've also prepared a second sub-program, so to speak, which is a Lorentz attractor in this case. You may also find an application note on the Lorentz attractor with a detailed description of the actual setup. The Lorentz attractor is set up with these blue patch cables here. The Lorentz attractor is much more normal, so to speak, than the Chua attractor, since it relies on multiplication as the nonlinear element at the basis of the attractor function, where the Chua oscillator uses this strange function f with its two absolute value functions. To see the result of the Lorentz attractor, let's switch the analog computer back into continuous operation. It's now running, and you see again the Chua attractor, and I will now select the second input set of the oscilloscope, and now you see a projection, a two-dimensional projection of the Lorentz attractor. You may wonder how values were typically read out from an analog computer. An oscilloscope display is beautiful but allows no fine-grain resolution when you are interested in certain values. And nearly all analog computers feature some kind of a digital voltmeter to read out values to a high degree of precision. And the digital voltmeter used in this machine is particularly interesting, as you can see. First of all, the display is really strange. It's a projection display. You have 10 incandescent light bulbs behind each digit, and you have a not really simple projection mechanism and a slide with the etched numbers of 0 to 9 behind each digit. And maybe you can hear the constant clacking. The decoding of the output of the analog digital converter, the decoding to base 10 to control this ADC display, is done by a relay tree. So whenever one digit changes, a couple of relay within the digital voltmeter changes. So the actual conversion from analog to digital is done with transistorized logic, but this was way too expensive back then for implementing a decoder for a 4.5 digit digital voltmeter output. So they did this with a really interesting relay contraption. Let me show you a more modern analog computer. What you see here is my laboratory prototype of a modern modular analog computer. This machine is still programmed with patch cables, but it's built from modern surface-mounted devices. What you see here on top is the power supply. That's pretty boring. Below you have a chassis holding the hand-soldered prototype modules, for example, a logarithm module or a trigonometry module or a module with 4 absolute value circuits and so on. And below, the chassis hold actual production modules. And what you can see here, for example, is on the left the manual control unit. Here you can select how to operate the machine, for example, continuous operation or repetitive operation. Then you see 2 modules with 8 manual potentiometers each. The next chassis holds a quad integrator module, and you can see that you can set the time constants of the integrators, the time scale factors in the range of 1 to 1000, as with the Telefunken RA770. Here you have another module with 8 manual potentiometers, 8 multipliers, another 8 multipliers, 8 summers, 4 additional integrators, 4 other integrators, 8 summers, and a quad comparator module. The program you see here is much more involved than the basically pretty simple Lorentz attractor or Chua attractor program. What this program implements is the simulation of a chaotic double pendulum. So you have a pendulum rod which is mounted to the tip of another pendulum rod which is mounted on some pivot point so it can swing freely around. You can find an application note describing the mathematical derivation of this double pendulum system and the scaling process and the actual setup of the analog computer. What I will show you now is the result of the actual simulation of a double pendulum using this big and modern analog computer. The problem is scaled so that one simulation run, which is pretty much real time, needs 9 seconds to complete, and the computer is set up to run in repetitive mode. So when I now press run repetitive, you will see the display of a double pendulum which then chaotically unfolds as it falls down. A standalone analog computer like this is of pretty limited use nowadays. What is desirable is to have a so-called hybrid computer, that is a combination of a digital machine and an analog computer. Since the analog computer is at its heart not a general purpose machine like the digital computer, it will mostly act as a coprocessor to the digital machine. The analog computer can, for example, take over the solution of hard mathematical problems, solving some horrible systems of coupled differential equations or whatever, while the digital computer, for example, controls the settings of coefficient potentiometers, which are nowadays, of course, digitally set coefficient potentiometers and no longer motor-driven potentiometers. And the digital controller, the digital computer, can also read out values from computing elements or sample values during a computation, which can then be post-processed by the digital computer. What you see here is a so-called hybrid controller module. That is a typical module of our analog computer system, and you can see the hybrid controller is based on an Arduino system on which a very simple monitor software is run, which controls the analog computer, and the communication to the host digital computer is performed via a USB connection. What you see here, these two modules is our in-house standard, so to speak. These two modules contain 4 digitally controlled potentiometers with 10 bits resolution each. Here you have a 16-bit precision analog digital converter, and you have a little bit digital logic, which is required to select any of the computing elements being part of the computer setup to be read out by the analog digital converter. The system you see here is actually part of a hybrid computer setup. It's coupled with a digital computer by means of this hybrid controller unit, and you see the USB device name on the label, and you have, that is pretty useful too, you have an additional module which features 24 digitally controlled potentiometers. So this setup, which currently represents the simulation of a water molecule, this setup has no manual potentiometers at all. All the potentiometers are digitally controlled, and as it's currently set up, you have 32 10-bit potentiometers being controlled by the attached digital computer, and the digital computer can also read out the results of your simulation even in real time and display it on the digital computer, or do some post-processing as required by your particular problem. So how does the future look? The future will definitely not belong to analog computers with a classic patch panel. That's not suitable for the 21st century. The future will bring analog computers which are integrated on chip and feature multiple layers of so-called crossbar switches under control of the attached digital computer, which can then program the analog computer. What is needed for something like this is a comprehensive software stack which abstracts from the intricacies of the actual analog computer. So the midterm goal for the next 1 or 2 years is to develop a software stack which allows a user to specify his problem in an abstract way and have the digital computer synthesize a bit stream, which will then be used to set up the actual interconnections of the analog computing elements, set the digitally controlled potentiometers within an analog computer setup, and then let the analog computer solve the problem you want to have solved more energy efficient or more quickly than the classic digital computer could do. And after the analog computer has completed, the digital computer can read out the value from the analog computer and chip and perform any post-processing which may be required. This printed circuit board is a simple example how an analog computer on chip might be used. This board makes use of a so-called FPAA field programmable analog array, in contrast to its digital counterpart, a field programmable gate array, an FPGA. This chip in the middle is made by a company called Anodyne and is basically a very simple reconfigurable analog computer on chip. It is not really well suited for solving mathematical problems, since the interconnect used by the manufacturer is based on so-called switched capacitors, so you lose one of the main advantages of an analog computer, namely continuous time. But if you want to get some first-hand experience on how to work with something like an analog computer on chip, you may, for example, use a board like this to make your first experiments. There are already Python libraries which support these chips from Anodyne, and these boards can, for example, be easily set up to yield coupled oscillators and mixers and whatever you need. I hope you enjoyed this quick tour on analog computing with some historical background, and thank you for your interest and your patience, and wish you all the best and happy analog computing.